Hello, this is Gary Eckmeyer. I wanted to make this video of my image model theory because the slideshow has a little bit more information in it than the Audio Express article that is out this month, September. It's called An Image Model Theory for Stereophonic Sound, and I've been working on it for about 40 years now. How to say it better. And I want to say a couple of things before I get going. I'm going to say a few controversial things that you may or may not have heard before, but I want you to hear me out, and then I'd like to make it more interactive, so I would encourage questioning, and you can stop me because I want to try to step you through a certain critical middle section of this thing, and I would like to have some participation.
Go for it.
I'm going to say that stereo theory has less to do with the human hearing mechanism than it does with sound fields in rooms. This is important because the confusion between binaural and stereophonic has stumped loudspeaker development for the last 50 years or so, and I'm trying to figure this stuff out too, and I wish that I could have a little help from the world with it, and so my presentation. I'm going to show you the history of human hearing research for a reason. Number one, to show how much work has gone into psychoacoustics and how we hear directions. And then I want to go into auditory perspective systems, where we put that knowledge to use. And then the speaker positioning gets down to some practical rules about engineering sound in rooms. The Greeks didn't even understand how you could hear something that was way over there from where you were. They called it the there-here problem. Well, they didn't call it, but our modern researchers called it the there-here problem. How can you hear that instrument when you're standing over here? They didn't know about sound going through the air and stuff. So here's some elements of psychoacoustics that have been done throughout the years. Fechner in 1860, he was there, Blauert. He asked, how can you localize sound when there's no dimensions of space? I don't know what he means by that, but they struggled with questions like these. Strutt and Rayleigh, 1876. The phenomena of binaural audition, Thompson, around 1878. Localization of actual sources of sound, 1934. Experimental psychology, head movements and vestibular something or other in sound localization, Wallach, 1940. Head movements. This guy Wallach set up a bunch of speakers, and he operated signals into each one to see how well we could localize which one was making that sound. This is MLD, I think, 1948. Masking level differences. Jeffress in 1947. All these guys are trying to figure out how in the hell we can hear direction so well. The precedence effect. They started figuring out the sound that comes first is the one that takes precedence in localization. Okay, auditory perspective systems. Obviously, research into psychoacoustics is linked to human hearing mechanism. Coding of spatial position, this, that, and the other, pinna, auditory canal, eardrum, HRTF, all this stuff. When it came to stereo, naturally they're going to assume that we need to study human hearing in order to reproduce these sounds if we want to use speakers and stuff. Say, in any book you've ever opened on stereo starts out with a human hearing mechanism, right? You got two speakers, two ears. You can hear any sound and anywhere in between those two speakers by means of summing localization. Two speakers, two ears, right? Okay, that's all we need to know. We're done. Put the sound from two microphones into two speakers and send it to your ears, and the ear brain takes care of the rest. Harvey Fletcher and William Snow, stereo and binaural are going to be continually confused with each other. This is Clement Adder's experiment, and obviously it's a binaural experiment. I don't know what he used for microphones, but the receivers were two telephone receivers in the audience's availability. And so you see how they wrote that up. The theatrophone is telephonic transmission where listeners received a separate channel for each ear, enabling stereophonic perception. It was this invention which gave the first stereo transmission of opera performances. It was really binaural, but they didn't know the difference, and they still don't. Alan Blumlein, a brilliant man, came up with Blumlein microphones, the 45-degree cutter heads for discs, right? A lot of stuff. Two speakers, 60-degree triangle, two ears. We're done. The classic stereo geometry based on equilateral triangle. Bell Labs had a little bit of a different idea. They had the curtain of sound. Does everybody know what that was? Probably we all do. They envisioned auditory perspective systems as a curtain of an infinite number of speakers that could simply relay the sound waves from the stage out to the audience with the same directionality as the original sound that was on the stage, simplifying that down to eventually 3 speakers. But most of the world was 2-channel officially because of limitations in technology and the availability of stuff that you can buy and materials. We were kind of stuck on 2-channel stereo for quite a while, and we were quite happy. So the development of better and better stereo seemed to resolve itself down to a search for greater and greater accuracy. The accuracy of what? Compared to what? The most difficult concept in audio is trying to put over what is the object that we are trying to reproduce. Is it microphone signals? No. It's an acoustic event that occurred in front of the microphones. It's not signals for the ears. It's the sound in rooms. I think everybody has agreed with that so far.
Yep.
Okay. So we've been making sound with directional speakers in boxes with all the drivers on the front until something happened.
901.
If you read no other papers on stereo or speakers or anything else, I would recommend this. This is the 1968 paper that Bose wrote to explain all about the reverberant field, the direct field, what it is that we hear when we go to a concert, the whole deal. This is the two papers that were published as one in around 1973 that attempt to explain the development of the 901. And you guys are old enough, along with me, we're all old enough to remember the impact that the 901 had. Some might disagree with that because they didn't end up liking that particular speaker, but it built a factory on a mountaintop, and it was quite a thing when it came out. But my problem was I was an original 901 owner, but I went to England and I started reading all this stuff that those folks wrote about stereo imaging. I said, what the hell are they talking about? Stereo imaging. All right, you can tell where everything is on the stage, right? Okay. Can I hear that? And I had to admit, no, I can't hear it with these speakers. It's very spacious. It sounds pretty good frequency-wise, but I can't pinpoint the soloist.
Did you do that in a auditorium?
No, in my room, in my house in England, where they have hard plaster walls. I had my speakers positioned like the owner's manual recommended, a foot and a half from each wall, the front wall and the side walls. So I was about to go out and listen to some quads or something, and I decided to hesitate for a minute and move my speakers around and see if I position my speakers the way these blokes do their speakers, would that make any difference? So I moved them out a couple of feet and in a couple of feet closer together, and holy mackerel, I fell on the floor. All of a sudden, the center soloist was a tightly focused little ball of sound that sounded like a head floating between the speakers. That's the image in my mind was this person is all of a sudden standing there singing. And I said, holy crap, it's not, the reflected part is not a problem with imaging, it's what causes the imaging. And as you move the speakers around, it moves the reflections around. If I could just figure out what scheme to use in order to make this perfect, I could, but the first thing I had to do was to write to Bose and tell him he's got to change his manual. So eventually, long story short, I got to the factory. I met him, and he wasn't going to buy that he should change his manual to make people put speakers in a certain spot or they wouldn't sound good. And then their chief engineer, Joe Varanth, pulled me aside. He says, you know, if you want to understand reflected sound easier, you don't draw spider webs of reflections. You'll never figure out anything from that. You draw the reflections as mirror images of the speakers on the other side of the walls. Then you can see where the reflections are positioned. I said, wow. I went home and I tried to figure out what would be the best way to draw where speakers should be positioned because of the way their early reflections positioned themselves. So I figured it all out. Go ahead.
I just want to interrupt for a second and say, tell me you were listening to an acoustic event that was recorded.
Yes. Well, it doesn't matter.
Okay.
The center
As opposed
soloist.
to a studio hyper-mixed event. Is that what you mean?
Right,
Yeah.
right.
Yes.
Well, any recording. Anyway, it imaged finally when I put them in the position that I that I determined by listening was the way to go, which happens to be a quarter of the width of the room in and the same amount out from the front wall. So I wrote this all up and I called it an image model theory for stereo, um, and I put an assumption in there that all this time we haven't really had a stereo theory to work with. We've all been just free floating on our own. So here's the deal. You got to position your speakers a certain way. You got to have a certain direct to reflected ratio. You've got to you got to know where the reflections are going when you move speakers around, and so on and so forth. And that stereo has been confused with binaural all this time because we have always assumed that we need to mimic the human hearing mechanism, two speakers, two ears. And that is not the way it works. Well, they read that and they didn't believe a word of it. They said I'm crazy, so I had to, I went home and I published an allegory called The AES Goes to Mars. I'll let you read that there for a second. I wanted to make it 100 years after this, when the AES got a little smarter. Imagine this. We find out that there really are Martians out there, and there's Venus people and others. But they don't all have two ears like we do, but they do like music. And they can all go to a concert just fine. Doesn't matter how many ears they have or what their hearing mechanism is. They can all go to a concert and enjoy the same concert. But when it comes to reproduction, the Martians had been using trinaural headphones because that's all they knew how to do. And then they met these Venus guys who had 5 ears, and us with 2 ears, and they said, how can we make recordings and reproduce them for everybody to enjoy? Now, should I ask the group any answers on that one?
2 channels are all you need to start with.
2 channels are all you need, but what about the 3-eared guys?
You can derive a center channel from them.
I think you want to look at it another way. And Gary, I know you're going to go into this, so bear with me if I upstage you just a bit. Because Gary and I have had this discussion many, many times. There are 2 ways to look at sound and the way your brain perceives the sound. There is the quote normal way, where sound is produced externally from your head. And it is outdoors, in a room, whatever. It's produced externally from your head. Then there's the other way, where the sound is produced inside your ear canal, i.e. using headphones. And those 2 are fundamentally different.
Right.
If you are looking at sound that is created inside your ear, then your brain does not have any advantage of your individual head-related transfer function. And now you would have a problem with the Martians and the Venusians and the humans. However, if, as Gary is talking about, creating a sound field external to the air, then that sound field, whether a Martian walks in or a human walks in, they will perceive it with what they are used to since the day they were born, or maybe in the case of Martians hatched, who knows. Their brain has worked with their head-related transfer their whole lifetime, and therefore the sound field will be perceived through their individual head-related transfer. So if you can create the sound field, it should work for everybody. If you're talking about having headphones, that the headphones are in the auditory canal, then you have to have some way to reference everybody's individual HRTF. And some people are going in that direction, but that's not what we're talking about here. So I look at it as if the sound is created external to your head, then it is a field, and now what do you want to do to create a sound field? Regardless of what kind of sound field you want, what are you going to do to create the sound field? That's
Right.
Tom Homan's answer is the first thing you do is you create front wide channels.
well.
That,
All I'm trying to get across is that there is a difference between creating the sound in the ear canal versus creating it in a space. And
Right.
now I'll let Gary go into his
Okay, let me
method of how he creates a sound field.
let me continue with the development of this thought, because it's important to understand how to create an auditory perspective system in a room versus a binaural system. You might have a three-eared Martian. They might even have an ambisonic hearing system where they hear in ambisonic A or ambisonic B, or even 5.1 format or whatever. It doesn't matter what their hearing mechanism is. If they enjoy a live concert, they can enjoy a field type reproduction system. We got to go back to what I said was there are two ways to reproduce a sensory experience. That is, in your vision system or in your auditory system. Sensory experience, okay? Direct sensory input, like headphones, or you can reproduce the object itself and just let all the beings sit down and listen. For example, if you're talking about vision, you want to show these guys what Queen Elizabeth looks like. You can either take a 3D picture, but for the Martians, with their three eyes, it would have to have three lenses and be reproducible to him with three imagers, right? So that doesn't work. That's a direct sensory input where your hearing or vision mechanism matters. But in a field type system, if you reproduce the object itself as a wax sculpture of Queen Elizabeth, then everybody, every little character that wanders into your planet can go up to her and look her over. They can see what size and shape she is, what colors her skin and clothes were. And that is the object itself. For audio, we're talking headphones as a direct sensory input. Has to be created with a dummy head, right? That mimics the sensors of your head. The object itself is loudspeakers in rooms. And that's what we need to realize in order to do it right. You got a head-related system, binaural, versus a field-type system, stereophonic or surround. And I lump stereophonic and surround in the same type with field-type systems. If you can create the sound in the room, you've got the problem licked. It also involves acoustics, of course, because making the sound in another room requires the acoustics to support what you're trying to reconstruct in there. Stereophonic and surround sound are field-type systems which have nothing to do with the human, Martian, or any being's hearing system. Okay, this is the controversial part. But in order, what I'd like to advance everyone to is to study sound fields in rooms. You need to study direct to reflected ratios. You need to study the spectral and temporal and spatial characteristics of sound fields in rooms. Spatially, we need to talk about the direct, the early reflected, and the reverberant fields. For some reason, Bose only talked about the direct and reverberant fields. He left out the early reflected fields. I don't know why, and he wouldn't answer that, but he just, in a concert hall, you don't have much of an early reflected field, you just have the reverberant field all around, right? That may be why.
But the early reflections are incredibly important.
That's right.
The reason why he did not want to address it is early reflections can cause problems, other problems in the sound field. It can cause congestion. Your brain does not deal nicely with early reflections as it does with intermediate reflections, which are ambience, and late reflections, which are echoes.
Right. And in a concert hall, sometimes you got a 5 or 6 second reverberation time, right? But as long as it reverberates and falls off smoothly, it sounds really good. So we talk about spectral, which is frequency response, temporal, which is reverberation time, and spatial, which is, can you see this drawing?
Yes.
Okay.
What is spatial?
Spatial is the directions from which sound images come. You remember Siegfried Linkwitz's drawing here?
Mm-hmm.
It shows the reflections as a mirror image on the other side. Now, let's get down.
I don't know what mirror image means, well, really.
Hmm?
I don't know what mirror image means in this case.
If you can see this whole drawing, mine is blocked off by the boxes of our faces, but the sound reflects just from the nearby walls, just like light reflects from a mirror.
Okay.
I'll show
Except
you.
that the speakers are facing forward and the reflections are behind it.
Yeah, that's a problem with direct firing speakers, isn't it?
Yeah.
Okay, let's get down to basics on speaker positioning and engineering sound in rooms. What I have observed in all of the videos that I've seen of these guys trying to tell you how to do stereo is that they are completely unaware of the spatial nature of sound. When they move their speakers around, they talk about frequency response effects, and they do talk about imaging because everybody wants good imaging and can hear it when you get it, but they don't relate it to the early reflected sound in their rooms at all, as if they're not aware of it.
Can I interrupt for 1 second, please?
Sure.
Yeah, I just want to make one point. When you talk about reflected sound and you talk about reflected light, you have to take into account, if you're dealing with light, is the light collimated or is the light diffuse? And you've got the same situation with sound. Is the sound very sharply defined or is it diffuse?
Okay, I'll get to that in a minute. So for the YouTubers, I would offer a more organized engineering way of moving speakers around and designing speakers and relating the image model of the sound in your room to the image model of a typical live sound field. The broad categories of things that matter are radiation pattern, speaker positioning, and the acoustics of the room itself, the reflecting surfaces in the room. Like I said, if you try to imagine speaker positioning and stuff with the vector diagram technique, you go nuts. I like the image model, which shows the images of these 2 speakers create reflected images of 6 more speakers behind the walls around them. Now you can see the positions of everything.
speaker is away from the wall. Is that right? So you must have subwoofers in the system. Because the front,
Yeah. I
your
like
front pair are away from the wall.
I like the SAT sub system because it gives you more the flexibility of the radiation pattern in the satellites, but the subwoofers doesn't. The directionality doesn't matter that much. So my correct position is a quarter of the room width in from the side walls and out from the front wall. What that creates is a network of speakers and reflected images that are perfectly evenly spaced from each other. If you deviate from that, you can tell with a diagram of this type what happens to your sound. If you've ever wondered what causes a hole in the middle, here you go. Too close to the corners. Also, as Richard has alluded to, if you have speakers that are sunk into the walls or shoved into the corners like a Klipschorn or something, it can't have these extra images around it, can it? So maybe
Correct.
that's something to think about. Maybe if we take a look at the image model of live sound, this is a typical live sound. You can imagine the reflections of the instruments as additional sources on the other side of the wall. This is a technique in architectural acoustics that they use to design concert spaces, I guess. I mean, they could use it. It's not exactly a mirror image, but you want to get the spatial nature of the sound on the stage to have some spaciousness like this, right? If you compare that...
When you have multiple images, don't you get interference between them?
Only if you
Yes.
don't do the room right. For example, this is superimposing the image model of your speakers onto an image model of a typical live sound field. The spatial nature of the reproduction is the same as the live model. Now you see what I mean by spatial nature. The result is, if you had only box speakers, the imaging tends to be like this. If you have more omnidirectional speakers, it tends to image in a plane behind the actual speakers and from wall to wall in the front wall. And that is because of these extra sources, especially if they have more output to the rear than to the front. Sound familiar? Dipoles are a particularly interesting case.
I was going to ask you about them.
If you take a pair of good dipoles and position them as I suggest, and angle them in 30 degrees, the rear of them will also be angled out 30 degrees, and the corner secondary reflection will be at its strongest with that angle coming back to you, and it will happen to be, that will be the deepest and the widest part of your total sound stage, which if you turned this in any different way, you'd screw it up. Like a lot of people take their dipoles and they put them straight on, right? So the reflection is just straight behind it, and it just comes straight back out, and it misses the listeners, and it doesn't help with spaciousness or depth or anything else. These speakers sound particularly good, as a lot of audiophiles have said, and that's why. In classic stereo theory, the sound stage is an auditory event formed in the brain psychoacoustically by your HRTF and the direct sound sent to your 2 ears from the speakers, as accurately as possible, arranged in a stereo triangle in front of you. Image model theory, or IMT, the auditory scene, or stereophonic sound stage, is a sound event formed by the speakers and their early reflected sound, and is best illustrated with an image model drawing of the speakers and their first and second reflections. This is the room. These are your two stereo speakers. This is a drawing of the reflections of those two stereo speakers, drawn as additional images on the other side of the nearby walls, like mirror images, only with sound. This is the image model of speakers and room. All imaging takes place within this area for all speakers, depending on radiation pattern. My imaging is drawn as spots of red within the image field to show where the images seem to be positioning themselves. For example, if you had a strong direct field for your speakers, like most box speakers, this is where things would seem to be coming from. They may have tighter focus, but less spaciousness. Here's an example from the Bose 901. If there was more sound cast to the rear of the speakers, the image speakers at the back of the image field would dominate, and the sound would position itself somewhat like this. If you can adjust the direct to reflected ratio within your room by listening, you might be able to get a near perfect sound field that looks something like this. To do this, it would require at least 6 dBs more output to the rear than to the front. The image model has implications as to moving speakers around as well. You can see in the graphic that if you move your speakers closer to your front wall, you may be compressing the depth of image rather than helping anything. If you move your speakers farther apart, their reflections also come closer to your speakers, defeating the purpose. You get what is sometimes called a hole in the middle. Corner placement is about the worst situation, which would cause a hole in the middle and a clustering of images near the corners. In all cases, radiation pattern and speaker positioning modify imaging only and are not doubling reverberation. You're not hearing some additional echo that was not recorded. All that you are changing is the spatial response of the speakers in your room. You can think of it as a summing localization, kind of like the phantom imaging that you get between any two speakers, only this is between the speakers and the walls around them. If you take a piece of graph paper and draw your speakers in your room and their image model, you can see what's happening by examining such a drawing more closely. You can count the reflections and measure their distances and timings. Here we're showing the first and second reflections only, because the rest of them become so diffuse and die off during the reverberation time, which is less than a half a second. So these are the main ones, the early reflections that affect the imaging. We shape the image field with radiation pattern and, of course, speaker positioning. We want more output to the rear in order to light up the reflected virtual sources because of their greater distance from us. With normal reflectivity, we would need at least 6 dBs greater output to the rear for the virtual sources. This amount, of course, varies depending on your room, size, and acoustics. A variable directivity speaker would adapt the imaging to the room, varying mainly the direct-to-reflected ratio. The simplest form of a variable directivity speaker would be a box with drivers on the front and rear. You angle them inward and adjust the gain of the rear driver at least 6 dBs more than the front driver. If you happen to have a dipole, or you could switch the rear driver to a dipole configuration, then you could steer the side null in addition to changing the direct to reflected ratio. And your image model would look something like this. All imaging happens in the designated area as phantom images suspended from points in space rather than just a clothesline strung between your two speakers. It's adjusted by the direct to reflected ratio, speaker positioning, and radiation pattern. Surround sound can widen the frontal sound stage and extend the ambience and sound objects all around. What I suggest we can learn from all of this is that the sound quality of a loudspeaker can be specified completely in terms of only two parameters: frequency response and dynamic radiation pattern. By dynamic, we mean a variable direct to reflected ratio and a flat power response in the room. In this scenario, there is no axis to a loudspeaker, only radiation pattern. The pertinent frequency response criterion is power response, not axial response. The directivity index becomes nonsense. Variable directivity, direct to reflected ratio, can match the imaging to your room, just like variable frequency response can match the frequencies to your room. Speakers now become sound projectors, and image model theory replaces stereo theory. Thank you.